Okay, so it's 12 o'clock, we'll go ahead and get started. A few reminders to start us off. First one, here's my teeny tiny schedule. Let's see how much I can zoom in. So this is the course schedule. It's the last page of the syllabus. I'm bringing this up just because next week is kind of a funny week on the schedule. We're not in class on Monday because that's our day of observation for the National Day of Truth and Reconciliation. So there's no classes. That's not a day on campus. October the 3rd is a Tuesday. So that's just a regular Tuesday. October the 4th is the funny day. That's a Wednesday, but it follows a Monday schedule. So what that means is that people in Monday's lab have a lab period on Wednesday, because Wednesday is pretended to be a Monday. So make sure on Wednesday, October the 4th, you follow your Monday schedule, because that's a Monday. We're doing our problem session next week, so we'll have a problem session on the 4th and the 5th, because that's a Monday and a Thursday. So keep an eye on your calendar. We got another one of those funny days on October the 12th, and then another one on November the 17th. So there's a few of those for the whole semester. Assignment 2, I had a request for an extension, so I extended that by a few days. I don't remember how long, till Monday maybe? Anyway, I bumped that for a few days for people who need a little extra time. And then last, our first term test will be here before you know it. Why don't I put the schedule back up? That's the one circled in red. That's the 20th of October. So, you know, we're kind of getting close. We're not right on top of it. When I teach these smaller classes, I like to invite students, if they wish, to bring a sheet of notes with them into the test. So on the sheet of notes, so you can bring in one piece of paper to the test, 8.5 by 11 inches. Don't try and get tangly on me. So one 8.5 by 11 sheet of paper, single-sided only, please, so just the one side. You may write anything you want on that sheet of paper. I am not going to inspect it. So anything you think will help you, you may write on that sheet of paper. The only thing is, it has to be in your own handwriting. Okay, so you can't photocopy somebody else's, you can't cut and paste the textbook on there. So a sheet of notes in your own handwriting. Any questions?
Midterm, that's just 15 minutes, is it?
Yeah, it's the
Right,
class
right.
period. Yeah, so instead of having a lecture, we'll have a test. If I can book the lab out for the test, we'll use the lab instead of in here, just because we'll be a little too cramped in here. So I'll let you know where for sure. Okay, any other questions?
One more clarification. I think on this course shell it shows that it's 13th for the midterm, so I'm just You're saying it's 20th, so obviously it's 20th.
The syllabus here has got term test on October the 20th.
Oh.
Are you seeing something different from me?
I'll look at it after. I'm sure I've seen it.
Yeah.
Maybe I do that wrong.
Okay, like, I'm looking at the syllabus, I print one off and I keep it in the binder with me.
Yeah.
Yeah, so anyway, feel free to show me what it is you're looking at, we can clarify that. Okay, any questions? No? Okay, so let's get started for today. Last day we finished up our path difference problem, so our interference. We started with chapter 21, that's our electric charge, field, and force chapter. We threw out some of the highlights of things about charge that are the fundamental things to know. We thought about Coulomb's law. That gives us the magnitude of the force. You get the direction of the force by knowing that like charges, oh my goodness, like charges do not attract, they repel. And unlike charges attract. So that gives us the direction. Coulomb's law gives us the force. So we're going to keep going with the example we just got started last day. So we started last day with a triangular arrangement of charges. We had a small charge on the top, two bigger charges on the bottom. We've got an equilateral triangle. In our process, we know that the first step is we want to draw the forces on the charge we're trying to find the net force on. So we're asked for the net force on this charge, so we draw the forces on this charge. Second step in our process is use Coulomb's law to find the magnitude of each force. So we did that last day. We know how big these forces are. To find the net force now, we just have to do the vector sum of these two forces. So we'll get into that part next. To do our vector sum, we want to find the components of those forces, add the x's, add the y's, and that'll give us the net force. So to start, why don't we draw the components of those forces? So the x component of F2 is the part that lies along the x-axis, F2x. The y component is parallel to the y-axis, F2y. We want to use our trig, so we'll need to have an angle here, theta. So this angle theta right here is the same as this angle theta right here. Okay, just by the geometry of the situation, we've got that straight line and that horizontal, so those have to be the same angle. Do you know off the top of your head what the angle of an equilateral triangle is? I kind of figure most people will remember this, 60 degrees. The triangle all has the same length sides, and the total amount of angle, 180 degrees, has to be split 3 ways. So the angles are 60 degrees because it's an equilateral triangle. If it wasn't equilateral, you'd use your trig functions to be able to find an angle. We'll do examples like that as we go. Before I calculate those components, I'm just going to draw the components of F3 as well. So the x component of F3 points to the right, F3x. The y component of F3 points down, F3y. If you got to this step in the problem and you recognized that the forces were at the same angle, except one's up and one's down, they had the same magnitude. If you recognize due to the symmetry that the total y components were 0, and you just said that the y part is 0 by symmetry, that would be okay. If you didn't recognize it and you do the math, that's fine too, of course. So let's find our components. F2x is adjacent to the angle, so we use cosine. It's to the right, so it's positive. F2 times cosine 60 degrees. So 4,495 times cosine 60 gives us 2,247.5 newtons. F2y points up, so it's positive. It's opposite the angle, so we use sine. Put that through the calculator, and we get 3,892.8 newtons. Then we can find the x and y components of F3 as well. F3x points to the right, so it's positive. F3 times cosine 60 degrees. Exactly the same as the x component of F2, 2,247.5 newtons. The y component of F3 points down, so that one's negative, minus F3 times sine 60 degrees, minus 3,892.8 newtons. So you find the magnitude of the forces using Coulomb's law, then you use your regular trig, your 10-20, 10-50 strategy to find the components of the forces. Now we want to find the net force. That means we've got to add up the x's and the y's. So the net force is F2 plus F3. So the net force in the x direction is F2x plus F3x, 2247.5 plus 2247.5. So the net force in the x direction is 4,495 newtons. In the y direction, some of the forces in the y, F2y plus F3y, 3892.8 minus 3892.8 equals 0. So there's the net x and y components. Then when we find the net force, our answer is a vector. We do have to write it as a vector. We found the components. And just to finish, we see that the net force is the x component, 4495 with units in the x direction, so I have. Okay, makes sense? Yep,
Would that cause a rotation? Because all the other forces end up being equal, there's only going to be one force that doesn't cancel it.
so if ultimately these charges were released, if they were free to move, this thing would start to move to the right. Yeah, so if it wasn't pinned in place, it would start to move to the right.
The whole triangle wouldn't stay the same except for the right because
Well,
other
they're not
forces-
tied together. If everything is free to move, this one would start to move to the right. Yeah. And that could be a question we'd ask, like if I gave you the mass of this little charged particle, I might ask you for the initial acceleration, just use F equals ma. Yeah, there's a lot of other stuff I could ask. Okay, so we're gonna do one more example where things are not all in a line, but before we get to that next example, let's do one that's like our pre-class question. And we'll come back to this vector stuff. So in our next example, the math on this one is pretty straightforward. The conceptual part is a little bit trickier. So we have two charges on the x-axis. Charge Q1 is plus Q, charge Q2 is minus Q2. So this one's positive, this one is twice as big and negative. This one is at the origin, so we can go ahead and label that x equals 0 if we wish. So I'm putting my origin right here. Positive x is to the right. This one is at x equals 5 millimeters. So where can a third charge, Q3, be placed on the x-axis so that it would have no net electric force? So somewhere on this line, and I'm not going to accept at infinity because it's kind of an obvious answer. So a definite answer with a number of millimeters that we could measure with a meter stick if we wanted to. So let's think about what the question is asking us to find. So as not to experience a net electric force. So it's saying that the net electric force, sum of the forces, is going to be the force between charge 1 and this third charge, Q3, and charge 2 and this third charge, Q3. They have to add up to be 0. So that's the goal of this problem. When we're thinking about vectors, if they add up to be 0, that means these two forces, F13 and F23, they have to be equal in magnitude and opposite in direction. So there's the heart of the physics in this problem, is recognizing that those forces have to be equal and opposite. It's the only way to get them to sum to be 0. So now we have to find a place on the x-axis where the forces are going to be equal and opposite. So we have three choices. It could be here to the left of Q1, it could be in between the two charges, or it could be to the right of Q2. So we've got three choices. You've got to look at each of the three spots and figure out which is the correct choice. When I ask people to I'll use the word guess. When I ask people to guess their first thought of where the spot might be, people typically pick in between the two charges. So let's just look at that zone first and see if that's the spot that's going to work for us. So let's see if that's the spot that's going to work. So let's take our charge Q3. I'm going to assume that my charge Q3 is positive. When we make an assumption in a problem, we should always write our assumption down. And at some point when we go through our workings, we should revisit our assumption and ask, was that a sensible thing to do? So I'm going to make the assumption. It has to be positive or negative. I do have to pick one, but I'm going to write it down. And later on I'm going to ask, was this okay? Would my answer change if I chosen negative? So my first spot I'm gonna pick will be in here between the two charges. So this is my charge Q3. What's the direction of the force on Q3 because of Q1? Or I believe Q1 and Q2. Okay, so is this one gonna feel a force to the right or to the left? To the right. So it's repelled by this one, so it's gonna be pushed to the right by charge 1. So there's the force by 1 on 3. What's the direction of the force on Q3 because of Q2? To the right, because it's attracted to this -1. So force 2, 3. So we could find a spot in here where those forces have equal magnitude, but they're not opposite in direction. Okay, so not opposite. So our answer is not here in the middle between the two charges. So we can get rid of that one. Let's look at another spot. Let's look out here. So I'll put my charge Q3 right here. What's the direction of the force on Q3 because of Q1? To the right, so it's repelled, so it's to the right. Right here, my charge Q3 is very far away from a small charge Q1. Is that going to give us a big force or a small force?
Small.
That's going to be a small force because it's K Q1 Q2 over R squared. So a small Q and a big R leads to a small force. That means I'm going to draw a small arrow. Okay, what's the direction of the force on this one due to this one? To the left, it's attractive. This time, we're very close, a small distance from a big charge. Is that going to give us a big force or a small force? That one's a big force. So there's F 2, 3. So out here in this spot, the forces have opposite directions, but they're not equal. So this can't be the spot. Okay, everybody good with that idea? That gives us one spot left to the left of Q1, so let's have a look at that place. So I'll put my charge Q3 right here. Let's look at each of those forces. So the force on Q3 because of Q1, it's going to be to the left because it's a repulsive force. This time, we're kind of close to a small charge. Is that going to give us a big force, a small force, or a medium force? I'm thinking about medium, right? We've got a small charge, but we've also got a small distance. So I'll draw a medium force here. F1, 3. The direction of the force on 3 because of 2 is attractive, because we've got the plus and the minus. This time we're far away from a big charge, so we get a medium force again, right? So the charge is big, but the distance is also big. Those are going to balance out to give us a medium force. So in this spot, we do get equal and opposite. That makes out here somewhere is the spot that's going to be the right spot. Yep.
We do also make an assumption on the size of the charge of Q3. Because how do we know that it's small? How do we know it's not like 2 Q?
Okay, so that's a good question. We never said what the size of Q3 is. And that's kind of a good point because the size of Q3 will affect the size of the forces. But however it affects it, it will affect both of them the same way, right? Because it's Q3 times Q1 or Q3 times Q2. So whether it's big or small, it'll affect both forces the same way. But we'll come back to that idea again as we start to do the math. Okay, so we've definitely dealt with the opposite part. We now know it has to be out here. It has to be out here somewhere, so now the question is where out here? So let's try and find the exact spot. So right off the bat, I'm just going to call my distance between Q3 and Q. I'm just going to call this X. So there's a symbol I have to use in my algebra. So now I'm gonna write down what it means that the forces are equal. If the forces are equal, it means the magnitude of the force between 1 and 3 is equal to the magnitude of the force between 2 and 3. Okay, so right here we're dealing with magnitudes of forces because we know they have to be the same size. Let's fill in our Coulomb's law of business next. K times Q1 times Q3 divided by the distance between 1 and 3 squared equals K times Q2 times Q3 times the distance between 2 and 3 squared. Let's simplify first. So I notice that I've got K on both sides. I can divide both sides by K. The next thing I notice is that I've got the magnitude of Q3 on both sides. So your Q3 actually cancels. If Q3 cancels, and we're only using the magnitude of it anyway, that means the sign didn't matter. And the size doesn't matter. So if we revisit our assumption that Q3 was positive, that's fine. We'd get the same result when we got to this step if Q3 was negative because we're using the magnitude of the charge. And then the size of Q3 doesn't matter because that divides out as well. So our assumption's okay. We did fine there with that. Okay, let's keep going. R13 is the distance between charge 1 and charge 3. So this is R13, that's the same as X. R23 is the distance between charge 3 and charge 2. So R23 is going to be X plus 5 millimeters. Okay, and we see that from the picture. R23 is from here to here, this much is X, this much is 5 millimeters. So let's get this business in over here. The size of Q1 is plus Q. So I've got Q here divided by X squared on the bottom. The size of Q2 is 2 times Q divided by X plus 5 millimeters squared. All right, a little bit more canceling to do. These Q's cancel. Next, we have to do some algebra. There are two ways we can do the algebra here. I can cross multiply this up to this side, this up to this side. You'd see that we get an X squared term and an X term, and we'd have to solve a quadratic. If you like that, that's fine. I see a shortcut here, which is to take the square root of both sides. So you can take the square root of the top and bottom of both sides. When you do that, you get 1 over the square root of X squared, which is X, root 2 over the square root of X plus 5, which is X plus 5. Right, so this just saves us having to solve quadratic, which I don't like to do. Now I'm going to cross multiply X plus 5 millimeters equals root 2 times X. I want to solve for X. So 5 millimeters equals root 2 minus 1 times X. X is 5 millimeters divided by root 2 minus 1, or 12.1 millimeters. Okay, so if we go to 12.1 millimeters to the left of Q1, a charge there will have no force, will feel no force. So let's just write our answer down to sum up. Place Q3 at 12.1 millimeters left of Q1 to have no net force. Okay. Questions? A lot of physics in that little problem. Okay, so let's go back to an example that has things on angles. So in this problem, we have 4 charges. Each charge has a magnitude of 1 microcoulomb, and the sign is as shown, so 2 pluses on top, 2 minuses on the bottom. They're arranged on a square with a side length of 1 centimeter. Find the net force on an electron that we would place at the center of the square. So we're going to use the steps that we wrote down in the triangular charge problem. We're going to follow those steps, and we're going to get to our answer. I want to draw the forces on my electron at the center. This diagram is a little bit small, so I'm just going to put it on the diagram I blew up on the next page. So there's my same diagram. I'm just going to draw on this one because it gives me a bit more room. So I'm going to label my charges 1, 2, 3, and 4. So Q1 is, oh wait, they're already labeled. So this is Q1, Q2, Q3, and Q4. Charge Q1, this electron is negative. So this negative charge will be attracted to this positive charge. It will point straight towards it. So there's my force due to charge 1. I'm going to call that F1. My force due to charge 2, it's going to be attracted to that one as well. F2. Due to charge 3, this is an electron, it's negative. It's going to be repelled by this negative. So there's my F3. You could probably argue that F3 should be right on top of F2. That would just be really difficult to see. My Sharpies would start to blend into each other. Typically, you draw them side by side close together, even though they are technically on top of each other. And then my force from charge 4, this is negative, that's going to be repelled as well. There's my F4. Okay, everybody okay with the picture? So these are the directions of the forces. What you might notice here is that we're at the center of the square. All of these charges have the same magnitude. All of these distances are equal. There's going to be a lot of symmetry in this problem, okay? And it will always save you time to take advantage of symmetries. So we said step 1 is to draw the forces. Step 2 is to find the magnitudes of the forces. I'm going to go back to my previous slide and find those magnitudes. So the magnitude of my force, F1, is K times the magnitude of my charge, Q1, and this was Q1, equals plus Q, times the magnitude of the charge on an electron, divided by the distance between them squared. I'm going to call that R. R is my distance from here to here. This is a value I can find using the geometry of the problem. So this is a square with a side length of 1 centimeter. So let's say this is D equals 1 centimeter. My arrow is from one side to the center. So the length of this side, this is also D equals 1 centimeter. The length of this side is D over 2, or 0.5 centimeters. The length of this side is D over 2, or 0.5 centimeters. The other thing you could do is find the length of the diagonal, and R would be half the diagonal. If that's where your brain goes, that's fine. So R is equal to the square root of D over 2 squared plus D over 2 squared, where D is 1 centimeter, gives us 7.07 times 10 to the minus 3 meters. Okay, so that's the distance between the center of the square and the corner of the square, between Q1 and the electron. K is 8.99. times 10 to the 9 newtons meters squared over coulombs squared. The magnitude of charge 1 is 1 microcoulomb, 1 times 10 to the minus 6 coulombs. The magnitude of the charge on an electron, so QE is negative E. The magnitude of that is just E, which is 1.6 times 10 to the minus 19 coulombs. Dividing that by a distance squared, 7.07 times 10 to the minus 3 meters squared. Okay, so there's all of our numbers. When I do that in the calculator, the magnitude of my force, F1, is equal to 2.88 times 10 to the minus 11 newtons. Okay, then let's look at our diagram. All those forces, let's see, the electron is the same distance from each of the charges, because for each case it's from the center of the square to the charge. Each of the charges 1, 2, and 3, and 4 have the same magnitude, so all of those forces will have the same magnitude. So equals to the magnitude of F2 equals to the magnitude of F3 equals the magnitude of F4, and then we say our reasoning, which is by symmetry. Okay, so always put in that you know it's true from the symmetry of the problem. If you don't catch the symmetry and you do the calculation, that's fine. It'll take you a little longer. You get a little more used to your calculator. No problem. You still get the same answer. So we've got the magnitudes of each of our forces. The next thing we need are the components of each of our forces. So I'm going to go back to my diagram and draw the components, and then we'll see what we can do about those. I'll put this up here. So for my forces, F1 points to the left and up. There's F1x and F1y. My F4 points left and up. My diagram's getting a little bit full, but hopefully you can still see everything. So F4 is left and up. F4y, F4x. F3 is right and up. And F2 is right and up. So there's all of our components. If we want to find components, we need to use an angle. So let's label our angle theta. So our angle theta is here. That's going to be the same angle that's over here. This cuts on the diagonal of a square. Theta has to be 45 degrees because it goes across the diagonal. So theta equals 45 degrees. You can figure this out from the trigonometry if you prefer. So I'm just going to come back to this diagram. So our angle theta here is our angle theta here. Okay, so this is our horizontal, this is the line going up to the corner, this is the angle theta. Tan theta is the opposite, d over 2, divided by the adjacent, d over 2 equals 1. Theta is the inverse tan of 1, which is 45 degrees. So if you didn't catch that just cut the diagonal of the square to recognize that it's 45, if you did the trigonometry, you would see that it was 45. It's still going to work out. Okay, are we good to here? Okay, to do our vector sum, we've got to write down all the components. So let's look at our components next. See how much I can get on the screen at the same time. So let's make a list of our x components and our y components. F1x is minus F1. I'm just going to call all of these f for the moment. So minus f times cosine 45. F1y points up, so it's plus f times sine 45. For F2, F2x points to the right, it's positive, plus F cos 45. F2y points up, it's positive, plus F sine 45. F3 is right and up, so the x and y components are positive. And then our last one, F4, is left and up, so the x is negative and the y is positive. If you looked at the diagram, you might recognize that the x components cancel, so you might just say that the net force in the x direction is 0 due to symmetry. That would be fine. I went through this process just to give you a structure on solving these problems. If everything didn't cancel, you would be going through all these steps. So it's okay to use symmetry when it's appropriate, and then sometimes you can't use it and you would go through these steps. So right here, we see that the net force in the x direction equals 0. The net force in the y direction, so you'll notice all 4 of the y components are the same, so it's just 4 times this one. Yep. I'm sorry, I didn't quite catch your question. Oh, so the units?
Yeah.
I think when you get into problems, particularly with force and newtons, a newton is an SI unit, so it's kilograms, seconds, and meters. Everything should go in meters. I think you'd get tangly if you left it at centimeters, because you wouldn't have a newton for your force unit anymore. Yeah, that's a good question. Yep, so SI units the whole way with this sort of problem. So the sum of the forces in our y is 4 times one of these forces. Put that through the calculator. 4 times 2.88 times 10 to the minus 11 newtons times sine of 45 degrees gives us 8.14 times 10 to the minus 11 newtons, and then we write our answer as a vector. The net force is 8.14 newtons times 10 to the minus 11. Point straight up, that's the y direction, or j hat. You're not asked to, but you could draw the net force on this picture if you wanted to. It would point straight up, and it would be 4 times longer than any one of the y components. So you could draw that if you wanted to. I would say that often on a test problem, I would certainly at least try and give you some symmetry just to cut the amount of time that you're working through stuff on your calculator, and to take advantage of that symmetry when you could. Okay, questions? Okay, fantastic. Oh, time is flying, isn't it? So that's our electric force. People who did high school physics, did you cover electric field in high school? Is that a concept? Okay, so it's not totally new. If you came to this course from doing Physics 1020, it's probably a new idea. Otherwise, you've heard of it before. We're still going to go through it and talk about what it means. So electric field, so if you did Physics 1020 or 1050 with me, every time we drew a force, I was very adamant that you had to identify the agent of the force. So you draw the weight vector and you identify that's the earth pulling down on something. You draw a tension vector and you recognize that's a string pulling on something. If you're pushing on something, that pushing force is your hands pushing. So it's always important to identify what makes a force. So when you talk about what makes the gravity force, you say, well, the earth makes the gravity force. The earth pulls down on a falling apple. Well, that's kind of weird. How does that work, right? Because the earth doesn't have a hand that it pulls the apple with. That's when we get into the idea of fields. So when you have gravitational force and an electric force, those are called long-range forces, or sometimes action at a distance. They're forces that happen without touching, so those are field forces, and that's where we're getting with this. So if you have a mass m, it's going to feel a gravitational force, and the gravitational force is mass times 9.81 meters per second, which points down. So g was always called the acceleration due to gravity. Now we introduce the idea that it's actually called the gravitational field. And if you've come across a little bit of reading about general relativity, you'd read about gravitational fields there, and that has space-time is curved and all that stuff. So that's kind of where it's discussed a lot. This gravitational field is the agent of the gravitational force. That's what makes it feel the force. The field provides the force. We define the gravitational field as the force per unit mass, and this field G is made by the Earth. And G fields, gravitational fields, they're not just made by the Earth, they're made by every body that has mass. So things that have mass have gravitational fields around them, including all of you people. It's just if the mass is small, the field is tiny and you don't really feel it. So for a picture of a gravitational field, I grabbed this off Wikipedia, I think. So the gravitational field around the Earth, you see it kind of points in. So anytime you release an apple, it's going to fall along the line inwards. The moon also has a gravitational field. When you're really close, it points in. And then when you're sort of out in the middle, they affect each other and they come together to make a total field. So you have gravitational fields around massive bodies. And the gravitational field is the agent of the gravitational force. Okay, so electric forces and fields are the same thing. So it acts the same way. We know that a charge Q feels an electric force because you can measure it, you can observe it. You charge up two balloons, you see that they won't touch each other. So we know there's an electric force. We know it's a long-range force, so we know there's an associated field. Rather than the gravitational field, it's the electric field. So the electric field is the agent of the electric force. So what we write is that our electric force, or let's say that charge Q, so some small charge Q feels an electric force, F, which is the charge itself times the electric field. So E is the electric field. It has units of newtons per coulomb, and it is a vector field. Okay, so E is called the electric field, the units, the vector. E is the agent of the electric force. It's the means by which the charge feels the force. So just like the gravitational field is the force per unit mass, the electric field is the force per unit charge. Okay, so electric fields go with charges, gravitational fields go with masses. And this electric field, so the gravitational field is made by something with a big mass, the Earth. The electric field is made by what's called a source charge. Okay, so that source charge is another nearby charge. It makes an electric field. This Q sits in that field and it feels a force. Okay, that's it in a nutshell. That's the description of it. Any questions before we get into figuring out how to use it and what to do with it?
Right there was force divided by charge.
Yeah.
So the electric field is measured in
Newtons per coulomb.
Just Newton coulombs?
Newtons divided by coulombs. So that's a Newton, that's a Coulomb, divide them and get the electric field.
Okay, but there's no like specific unit for the Newton Coulomb, or is it just Newton?
Just Newtons per Coulomb, it doesn't have a different unit. And one thing I'll point out on this slide, notice that I'm not using absolute value of the charge. You include the sign of charge. That's because the force can be attractive or repulsive, so the force can point one of two ways. And the way the force points depends on the sign of this charge. So that's why we include the sign of the charge. So let's see about writing down what the electric field is. So our goal here on this slide is let's find the equation for the electric field near a source charge. Our source charge is going to be this positive charge. We call it plus Q. This is our source charge. So this is kind of a big charge. It's going to make a significant electric field. We want to find the electric field that has our symbol of E. It is a vector, so the direction is definitely going to matter. And this electric field is going to be made by this charge Q. So the first thing we do is we look at our charge Q and we pick some point P and we just label it. Really important here, P is an empty point in space. We're calling it P because we're pointing at it. Okay, so I can point to things that aren't here all day long. That's what we're doing here. So there's nothing here. It's just a point and we're asking what is the field here. The distance between this point and this charge, we're going to call that R. And our goal is to find what is the electric field here. So E equals. Okay, good with the idea? Just an empty point in space, we want to find the field. If we want to find the field, we know about the forces, so let's use the idea of a force to help us find the field. Let's place a small positive charge at our point P. So we're going to place a little charge Q at point P. This is going to be a positive charge. I'll even put my plus sign in here. So my charge Q, it's little, it's called a test charge. Some books would use the term probe charge, but test charge is more common. It has a small magnitude, and it is positive. Then we ask the question, does this little test charge Q feel an electric force? Our answer to that question is yes, of course it does. This is a positive charge, this is a positive charge. They repel each other, so this feels a force that pushes away. So our answer to that question is yes. It does feel a force. That force, the magnitude is given by Coulomb's law, K times the magnitude of Q times the magnitude of Q divided by the distance between them squared. The direction of that force is repulsive or away. I'm going to choose the word away. And by away, I mean away from the source charge plus Q. I am keeping an eye on the time. Even if we don't finish, I'll stop at 12:50, but I hope we'll get finished. So this is the force exerted on the test charge by the electric field created by the source charge. Okay, so that's what's happening here. If we want to ask what is the electric field, what we do is we remove our charge Q. So we take it away, we're left with our point P again, and we ask what is E? What is the electric field? And we know there has to be an electric field because it felt an electric force, and we know those two things go together. Well, we know that the electric field is the electric force divided by the charge. This is positive, so it means these two things have to point in the same direction. So my electric field is going to point away. The magnitude of my electric field is going to be the magnitude of my force divided by the magnitude of my charge. So K times Q divided by R squared over Q. Those Q's cancel, and I'm left with my electric field, is K times the magnitude of the source charge Q divided by R squared, where R is from your charge to your point. The direction of that is away from that positive source charge. Okay, I've got some comments to make about it, but it's 12:50, I know you have places to be, so we'll quit there, and we'll just kind of throw in a summary as we get started on our next class.